Alright. A soccer player kicks a ball with an initial velocity of 20 meters per second at an angle of 40 degrees above the horizontal. The ball must clear a 5-meter high wall located 20 meters away from the player. Assume the air resistance is negligible. So the first thing I'm going to do is I'm going to draw a picture of this. So we have a soccer player, and they are going to kick the ball with some initial velocity at an angle of 40 degrees above the horizontal. And this ball is going to have to clear a wall that is 5 meters high and 20 meters away from the player. So we're going to put a wall here. And if it's 20 meters away from the player, I can assume that my displacement in the x direction, right, my change in x, is going to be 20 meters, meaning that this is my initial and this is my final position. I also can assume that since the ball is starting on the ground and it has to clear this 5-meter high wall, that this distance is going to be my change in y, or at least the minimum change in y necessary. So now I'm going to write down all the information I have, right? So I have that my change in x, my displacement in the x direction, it needs to be 20 meters. I have that my displacement in the y direction needs to be 5 meters. I know that the magnitude of the initial velocity is going to be 28 meters per second. And I know that the angle that the ball is kicked at is 40 degrees. So now let's figure out what it wants us to find. It wants us to determine if the ball clears the wall and by how much it clears the wall. So let's say, what is the maximum change in height of this ball? We need to find the total time that the ball is in the air and the maximum displacement in the x direction. So how far is it land from the place that it started? So because we have an object that is going to be kicked at an angle, this is going to be a 2D kinematics equation. I also know that I have an acceleration in the y direction that's due to gravity, so that's negative 9.81 meters per second squared. And I have 0 acceleration in the x direction because there's no forces acting on it. The only acceleration that I have is due to gravity. So I'm going to go ahead and write down my kinematic equations. So now that I have my kinematic equations written down, I can start to solve this problem. So we want to figure out if this ball is going to clear the wall and by how much it clears the wall. So what it's really asking us for is to figure out what is the maximum height of this ball at the x final location. So I can consider when the person kicks the ball to be the initial condition and when the ball is above the wall to be my final condition, which means that I actually don't have this delta y information. This change in y, the wall being 5 meters, only is going to allow me to determine if the ball goes above the wall or if it bounces off the wall. It doesn't actually help me in solving this problem. So right away, I need to start to assess this problem and figure out where I can start. I'll be honest, whenever I first took this course, this was a really challenging problem. I've done this problem so many times that I know how to solve it. I know where I need to start. I know what variable I need to solve for and how to connect them together. But whenever you're first approaching a problem like this, it can be really overwhelming. So I'm going to try my best to explain my thought process. And in all honesty, sometimes this really is just a trial and error approach that students use. It can be time consuming, but you do learn a lot through that process, and it helps you know how to solve problems like this in the future. So first of all, I am going to rewrite all the information I have. I'm going to imagine that this wall is no longer there, that I just have this person here, they are kicking a ball, and I want to figure out what is this location whenever the ball is at 20 meters. And I know that my y initial is going to be 0 because the ball is starting on the ground. So the information I have is that my initial position in the y direction is 0. I want to figure out what this final position is. I have that my initial position in the x direction is 0. My final position in the x direction is 20 meters. I know that I have some initial velocity, and I can get the x and y directions from this information. And I know that I have an acceleration in the y direction and an acceleration in the x direction. So there's a few approaches that I could use to try to solve this problem. So let's just think about what we could solve for in the y direction, right? Because we want y final. Well, I need to find the final position. I have an initial position, I have an initial velocity, I have an acceleration, but I don't have time. Two unknowns, that's a problem. I don't have a final velocity in the y direction, but I have an initial velocity, I have an acceleration. I don't have my total change in position in the y direction. I don't have a final velocity. I have an initial velocity and acceleration, but again, I don't have time. And in this top equation, I'm missing 3, right? I don't have the final position, I don't have the final velocity, and I don't have time. So this means that I need to either figure out how long it takes for my object to get to that position, or I need to figure out what is the velocity of the object when it gets to that position. Either approach is fine. It is going to be impossible for me to determine what my final velocity is at that position unless I know how high this object is or how long it takes to get there. That means that only looking at the y direction, I cannot solve this problem. I have to consider the y direction and the x direction together. So I'm going to have to solve this problem as a system of equations, meaning that I'm going to have one equation that represents the motion of this object in the x direction. I'm going to have another equation that represents the motion of the object in the y direction, and I'm going to have to find a way to connect them together. But since position, velocity, and acceleration are all vectors, their x and y components are separate. I can't connect them that way. There is one variable in these kinematic equations that is not a vector, and that is time. Time is the only way that I am going to be able to connect an equation that represents the change in motion in the x direction with an equation that represents the change in motion in the y direction. So I have to pick an equation here and use that equation to connect these x and y directions together. So right off the bat, I'm not going to want to pick the second equation because it doesn't have the variable that I'm trying to solve for. I want to minimize how many equations I need to use. So I need an equation that has time, right? So this equation isn't going to work. I don't want to involve the final velocity because that would be an entire ordeal. So we'll get rid of that. And this equation, equation number 2, doesn't involve the final position in the y direction. So I can't use that. This means that I need to use equation 3 to represent the motion in the y direction. So I'm going to rewrite this so that y final is equal to y initial plus my initial velocity in the y direction times time, plus 1/2 acceleration in the y direction time squared. The next thing that I want to do, right, is I'm going to check off that I have this information, I can get that information, I have my acceleration in the y direction, this is what I am solving for. but I don't want to do anything with this equation yet. I now want to get an equation that represents the motion in the x direction that involves time that I can plug in for these t's. So I do have my change in position in the x direction, I have the acceleration, and I have the initial velocity in the x direction for this object. So I want to figure out which one of these equations is going to be the easiest for me to use for the x direction. Well, equation 3, if I want to find time, I'm going to have to use the quadratic equation. That's going to be a pain to plug in to my equation for y. I don't want to have to go through all of the quadratic equation to get something for t that gives me a plus or minus and I have two options. That's going to turn into a mess. That's not the approach we want. I can, though, use the second equation, even though I don't have... No, I can't. I cannot use the fourth equation because it doesn't have t, and actually I can't use the second equation either because since my acceleration in the x direction is equal to 0, my change of velocity will be 0, meaning that I would get a solution that says time is equal to 0 over 0, which is unhelpful. I have to use my first kinematic equation here to solve for time. So I'm going to rewrite this. So this means that x final is equal to x initial plus the average velocity in the x direction times time. I now want to rearrange this to find t. So this means that my change in x is going to be equal to the final in the x direction plus the initial in the x direction divided by 2, right? Because this is my average velocity in the x direction. So we add them together and divide by 2. And this will be multiplied times time. So now I want to get time by itself on the left-hand side. And this will give me that time is equal to 2 times my change in position in the x direction divided by my final velocity in the x direction plus my initial velocity in the x direction. We can actually simplify this a little bit more, right? Because our acceleration is our change in velocity over a change in time. If our acceleration is equal to 0, this means that our change in velocity has to be equal to 0. If our change in velocity is equal to 0, right, then our final velocity is equal to our initial velocity, meaning that my final velocity in the x direction and my initial velocity in the x direction are going to be the same number. This simplifies to 2 change in position in the x direction divided by 2 times this initial velocity in the x direction. I'm using initial velocity because I have that value. We can simplify this further, and we get that time is our change in position in the x direction times my initial velocity in the x direction. So now that I have an equation for time, I'm going to plug this in to my equation for the final position in the y direction. This means that my final position in the y direction is going to be equal to y initial plus my initial velocity in the y direction times my change in position in the x direction divided by the initial velocity in the x direction plus 1/2 acceleration in the y direction times my change in position in the x direction divided by that initial velocity in the x direction squared. This is going to be quite a bit of algebra, especially because we still need to figure out what the initial velocity in the y direction and the initial velocity in the x direction are. So I'm going to try to simplify this a little bit. The next thing I'm going to do is I'm going to replace my VIY and my VIX with their trig components. So the initial velocity in the y direction is going to be the magnitude of the initial velocity sine theta. Remember that I'm getting this from the trig triangle, where this is my 40 degrees, this was my initial velocity magnitude, this is the y component, this is the x component, so I need sine to get the y component, and to get the x component, I will use cosine. Now I'm going to plug these in to my equation. I'm going to drop the absolute value. I'm just going to assume that we all understand that if I don't have a subscript, it means the magnitude of that velocity. So y final is equal to y initial plus my change in x times the vi sine theta over vi cosine of theta plus 1/2 acceleration in the y direction times my change in position in the x direction squared over vi squared cosine squared theta. So I'm actually going to simplify this a little bit more before I start plugging in numbers, because the less that I have to plug into the calculator, the less likely I am to make a stupid mistake and have to redo the problem all over again. Okay, sine over cosine, that's tangent. So I'm going to go ahead and start plugging in numbers. So my final position in the y direction is going to be equal to the initial position, which was 0, plus the change in x, that was 20, tangent of 40 degrees, plus 1/2 times the acceleration in the y direction, negative 9.81, and I'm going to use big brackets here, times the change in position in the x direction, that was 20 squared, divided by the initial velocity, the magnitude of the initial velocity, which was 28 squared cosine. Oh, I can make this easier if I just plug it in like this. If I just do 28 cosine of 40 degrees and then square that whole thing, it'll be easier. I'm actually going to punch this in the calculator in multiple steps. That's because I am, again, less likely to make a mistake, and if I do make a mistake, it's a lot easier for me to figure out where I made the mistake, right? If I just start punching things in the calculator and I get a wrong answer, I have to essentially redo the problem again, and I don't want to do that because we've spent a lot of time working on this. So 0 plus, let's call this 16.8. I'm going to round it. Hopefully that doesn't bite us in the butt later. This is a negative sign, that'll come out, so it'll be 16.08 minus 9.81 times a half, 4.905. This will be times 400 over 460. And I'm going to punch it in the calculator again. Is 4.265. So my final position in the y direction is going to be 12.53 meters. So because, let's write that again, 12.53 meters. So because the wall is 5 meters high, this is absolutely going to clear the wall, but it asked us by how much does it clear the wall. So it clears the wall by, 7.53 meters, and that should be the solution to this problem. Part 1. The next thing it wants us to do is to figure out the total time that the ball is in the air. Well, the problem is that I don't know if it's at its maximum height when it's above this wall, or if it's rising or falling. I don't know how far it actually travels. So, how am I going to solve this? I could try to figure out how long it takes to get to its maximum height, and then how long it takes to fall from there. That's the only thing that comes to my mind. I'm sure there's another way to do this. I could try to figure out, right, if I consider this initial condition to have some initial velocity, right, 28 meters per second at an angle of 40 degrees, I could consider, like, let's say that the maximum height is here. I could calculate how long it takes to get to maximum height, and then from maximum height back to the ground. I can do that if I only consider the y direction, because the x direction, the velocity isn't changing at all. But in the y direction, we still have, right, you have an initial velocity vector in the y direction. Whenever it hits its max height, it has 0 velocity in the y direction, because then it starts to come back down and the velocity vector grows. So at its maximum height, our velocity in the y direction would be 0. It would still have velocity in the x direction, right? It's still moving, but it would have no velocity in the y direction. I think that that's the approach that I'm going to take. There might be a faster approach. This is just the one that popped into my head. So I'm going to first figure out, one, time to max height, and then max height, that's not how you spell that, and then time to go from max height to ground. So I am considering, right, the ball being kicked up until it gets to its max height, where the velocity is 0, and then I will do it again, starting with velocity is 0, and then some final velocity. Alright, let's do this. Let's just start. So I have the initial velocity in the y direction. I'm only thinking about the y direction because this is only valid for my y direction. I already calculated that. My initial velocity in the y direction was going to be 28 sine of 40. So let's round it. Let's call it 18 meters per second. I have the acceleration is going to be negative 9.81, and I am wanting, I have the final velocity, right? Duh, 0. So I can figure out time. I can solve this for time, and I can do that using the second kinematic equation, right? So I can do that using the final velocity in the y direction is equal to the initial velocity in the y direction times that acceleration in the y direction times time. I'm going to rearrange this for time. So time is equal to the final velocity minus the initial velocity divided by the acceleration. So the time to get to max height is going to be 0 minus 18 divided by negative 9.81, so close to a little under 2. Yeah, time is 1.83 seconds, and that's to get to max height. So then I want to go from max height back to the ground. This means that my initial velocity is going to be 0, and I have acceleration in the y direction is negative 9.81. I want to find time. I don't have the final velocity. No, I don't have max height either. I mean, I'm going to be honest. It's probably just going to be double the initial time, but I don't know that confidently without doing the math, so I need to find an approach to do this. I can just find the height, like how high is my object at that point in time, using the third kinematic equation. So I'm going to figure out how high this object is at that point in time. So y final is equal to y initial plus my initial velocity in the y direction times my time plus 1/2 acceleration in the y direction times time squared. I am looking to figure out what y final is because y initial is 0. The initial velocity in the y direction was 18. It is traveling for 1.83 seconds to get to its maximum height, plus 1/2, negative 9.81, times the 1.83 squared. And this is going to give us that the height at that point in time is going to be 16.5 meters. So then I can use this information that the change in height is going to be negative, right, because it's falling 16.5 meters, and I have an initial velocity is equal to 0. I can do this and find time. I can actually use that third kinematic equation again. Y final is equal to y initial plus the initial velocity in the y direction times time plus 1/2 acceleration in the y direction times time squared. I'm only doing this because I know that my initial velocity is equal to 0, so this t will go away, meaning that I won't have to use the quadratic equation. So my change in y is going to be equal to, this is going to go to 0 because my initial velocity in the y direction was 0. 1/2 acceleration in the y direction times time squared. I'm going to solve this for time, meaning that time is going to be equal to plus or minus the square root of 2 times my change in position in the y direction times acceleration in the y direction. Time can't be negative, so it has to be a positive, so this will be the square root of 2 times negative 16.5 divided by negative 9.81, and we get that our time is going to be equal to, you guessed it, 1.83 seconds. So the total time that this object is in the air is going to be 3.66 seconds. Could we have conceptually done this for at least the second half? Yes, we could have, but now that we did the math, we are confident that nothing unphysical has happened in this problem. Is this the most efficient approach? No. But you don't second guess yourself. So the last thing I want to figure out is what is the horizontal range of the ball? So how far does it go in the x direction? Oh, well, now that I have the total time, I can not use this equation because my acceleration is 0, so that'll go away. This is a pain. I don't really want to do that. This is not going to give me delta x. I have to use the third kinematic equation again. Why do we even have others? So x final is equal to x initial plus my initial velocity in the x direction times time plus 1/2 acceleration in the x direction times time squared. Because my acceleration in the x direction is 0, that last term goes away. I also know that my initial position in the x direction is going to be 0 because I set it to 0. So I can use the initial velocity in the x direction that I calculated earlier, which was 21.5 meters per second, and I can use that time that I calculated, which was 3.66 seconds, and I figure out that the total distance that this ball travels is going to be 78.7 meters. This seems like a very far distance for this soccer ball to travel. I don't have the solution to this problem, so work it out yourself and see if my answer is correct.